All right, welcome. This is going to be a real quick video on piecewise defined functions. But first, since we're going to be making a lot of graphs in this lesson, I think it would be good for us to review all the different function types that we've graphed in this class. So a constant function is like y equals some number k. And that's just a horizontal line, right? The set of all points that have y value equal to k. Linear is, we know all about that, mx plus b. Its graph is a line with slope m and y-intercept b. Absolute value, I'm going to just, for any of these where we could make them as complicated as we want, I'm just going to kind of go with the parent function. Y equals absolute value of x, that makes a v. With quadratic, y equals, I'm just going to do x squared, but ax squared plus bx plus c. This is another one that we're very familiar with. We're just going to kind of go up like that and make a parabola. Square root, like y equals the square root of x, that's a sideways parabola. Remember that, we studied those radical functions, and it kind of went up, but really leveled off. Kind of like the graph of log, but somehow very different, because really log is an exponential curve, and square root is a parabola. And we did a little bit of investigation on the relationship between those functions and their inverses and what happens with the graph. That's what's going on there. Y equals x cubed is a cubic function, and it looks kind of like that. Cube root. Okay, kind of like the graph of square root, except it's defined where x is negative, so it's got that other half. Exponential, like y equals e to the x. Always positive exponential growth. Okay, a log function like y equals natural log x, that's going to be the one that we're mainly concerned with in courses beyond Algebra 2, is going to look like that. It's got a vertical asymptote at x equals 0 on the y-axis. And then rational function like y equals 1 over x, we just learned about that in this class. That's the one that's got horizontal and vertical asymptotes. That was a pretty bad sketch, but these are the different function types that we've encountered so far in this class. So now let's talk about a piecewise function, because that's what we're here to talk about. This is a function defined piecewise, and what that means is it's defined in multiple pieces. And really for the domain where x is greater than 0, we're going to follow this rule. But if x is less than or equal to 0, we're going to follow that rule. And I don't know, something about this really speaks to me. It's kind of like life, certain rules apply at certain times. So the first question I'm going to ask you is, what is the value of f of 3? Now, the first thing we want to do if we're just given an equation and we want to find the value of a piecewise function is we have to identify, which rule are we going to follow. So I'm going to say x is equal to 3, and 3 is greater than 0. So as a result, I'm going to follow the x plus 1 rule. So I'm going to say f of 3 equals 3 plus 1, which is equal to 4. And so if you were asked something like, okay, what's the value of f of negative 3? We'd say, okay, well, we're plugging in x equals negative 3, and negative 3 is less than or equal to 0, so I'm going to follow the x squared rule. F of negative 3 is equal to the square of negative 3. Remember, if we're plugging in negative 3, we're squaring the negative and the 3, and that's going to be positive 9. And then I might ask you to sketch the graph of f. Okay, but these are two things that we already know how to sketch. We know how to sketch y equals x plus 1. We know how to sketch y equals x squared. So we're just going to sketch parts of both of those on the appropriate intervals. So I can see I'm not going to need a whole lot of, or any negative y's. So I'm just going to draw my axes this way. And if x is less than or equal to 0, y equals x squared. Okay, so I've got kind of the left half of this parabola. Okay. And since this is less than or equal to 0, that includes the point where x equals 0. And so we indicate that, it's going to be kind of hard because I'm using a marker, but we're going to indicate that with a filled-in circle. And x plus 1, well, that's a line with slope 1 and an intercept y equals 1, so I don't know, maybe I'll put that here. Okay, that's going to, I'm going to need an open circle there because that's going to be the beginning of this. And x is strictly greater than 0, so it doesn't actually equal 0, but it gets really close, right? Any x where it's positive is going to be on this part of the graph. So we'll get really close to that circle, but we won't actually touch it. Okay, and that's going to be a sketch of the graph of f of x. Here's another one we could sketch. So g of x equals 2 to the x when x is less than or equal to 0, and 1 minus x when x is greater than 0. Okay, so what I'm going to do, I'm thinking again, I'm not going to need much negative y space there. So I'm going to just make myself some axes. Think about, okay, the graph of y equals 2 to the x, that would be exponential growth, except I'm not going to have all of that growth. It's going to get cut off at the y-axis because x is less than or equal to 0. So I'm going to show that horizontal asymptote. I'm going to show some growth. Okay, and that's until x equals 0. Now, 2 to the 0 at the right edge of this point, or of this part of the graph, I guess is what I'm saying. The y-coordinate is going to be 2 to the 0. We know that 2 to the 0 is equal to 1, so I'm just going to label that there. And then when x is greater than 0, I have y equals 1 minus x. So that's a line with slope -1 and an intercept +1. So it's going to go down like that. And so these two pieces of graph happen to meet up at the point where they could have been, or where they were splitting. And we'll be interested in that situation here in a couple minutes. Or maybe right now. So now I want to talk to you about continuity. So in this class, our definition of continuity is going to be that a function is continuous if its graph doesn't have any jumps, holes, or vertical asymptotes. And I'll be really explicit about what I mean by those three things. We could also say in this class that a function is continuous if we could draw its graph in one kind of stroke of the pen without lifting your pencil off the paper, I think is what they say. And somehow that's a really good definition, but it's not mathematically precise. And then in calculus, we'll have a definition. And then if you keep taking these math classes, you'll realize that that's actually not the most robust definition either. And then you get the real one, quite a ways in the future. But somehow the most robust definition of continuity is at least easy to work with. So I'm going to just show you the three types of discontinuities right here. All right, so the first type is jump discontinuity. And this is something that's kind of new to us that we haven't seen very often, or maybe ever. But this is the type of thing that oftentimes comes up with a piecewise defined function. If I go back and grab where did I put that? If I grab the paper I was just graphing on, over here, this was a jump discontinuity because the graph jumped from here to there. Okay, I could not draw this in one stroke without picking my pencil up off the paper. I'd have to lift up and then go down over here. Okay, so that's a jump discontinuity. And the commentary I'd have on that is that this is often, but not always, caused by a piecewise defined function. I think I can write you down one formula for like a closed form equation for a function that has a jump discontinuity. I'm just going to bring that in right here and just show it to you once, and then probably leave it there for this class. We don't really need this function, but something like f of x equals the absolute value of x divided by x. If you think about that, what's going to happen with this function is it's going to be 1 for any x where x is greater than 0, right? Because absolute value doesn't do anything. I'm dividing it by itself. 0 over 0 is undefined, but if x is negative, then the absolute value of x is going to be a positive number divided by the negative version of itself is going to be -1. That causes a jump discontinuity. There are a couple others I know about, but none that are like kind of at the algebra 2 level. Okay. A removable discontinuity, that's a hole in the graph. Okay. But I want you to know that terminology, mostly because I'm going to ask you a multiple choice question on the test that uses that terminology. Okay, so I'm going to say this is a hole in the graph. And we know that that's, from the last unit, that's generally caused by, some sort of redundant factor in the top and bottom of a rational function where we could cancel it off. And so I drew you a picture of, a line with a hole in it, which is something I think we graphed on the test. But something I might also point out is that if we removed that discontinuity and then just decided to define the function elsewhere, that would still count as a removable discontinuity. Basically, it would be otherwise continuous except for this one point that got removed from the graph. And then an infinite discontinuity, that's just fancy terminology for a vertical asymptote. Right, we've seen these. We studied them in the last unit. We saw that occasionally they can both go up. I thought I might remind you about that. And it's caused by division by 0, specifically like a non-zero number divided by 0. That's really what's causing an infinite discontinuity like that. And one way I could ask you about this in Algebra 2 would actually be to, go to AP Classroom and pull out this AP Calculus multiple choice question that they ask sometimes. And we've got a piecewise defined function, and they say it's continuous at x equals 3, and they ask us to find the value of k. Now, if I was recording this on a tablet or something where I could do this really nice, what I'd say is, okay, we've got x squared plus 2 for x less than or equal to 3. Okay, so that's part of our graph. But then I've got this other piece, let me just get a scrap of paper or something, that's going to be a line, 6x plus k. And so that's a pretty steep slope, but I'm actually not going to even draw it that steep. So let me just kind of draw it like that. Okay, now what we're doing here, this is where x is greater than 3, so that's why I put an open circle there, is plus k will move this thing up and down. And what we're going to do is we're just going to find the perfect value of k that causes this to sit right on top of that filled in circle, causing this to be, like that, continuous. No break in the graph, no hole in the graph, no jump in the graph, no vertical asymptote. Okay, but algebraically speaking, how we're going to do this is we're going to take the two pieces, we're going to set them equal to each other. And we're going to plug in the x value that they share. So when x equals 3. Okay. So I'm going to say, all right, 3 squared plus 2 equals, so wait, 6x plus k. I was thinking that seemed too good to be true. 6 times 3 plus k. And I'll have 9 and 2 is 11, equaling 18 plus k. And I could subtract 18 from both sides, or I could just try to solve this one with my eyes. Either way, I'm going to say this is continuous if k is equal to -7. And then there's this other one where we've got 3 pieces of function, okay, which is definitely something that could happen. You could have any number of pieces of function. And you might be asked to find the values of a and b that make f of x continuous for all x. So I need to do the same thing, but at 2 different places. But notice how I've got 2 unknowns here. That's going to bring up a 2x2 system of equations. And, while this is not something I would be likely to ask you to do on a quiz or a test, you can bet I'm going to ask you to do it on the homework because we need to practice our systems of equations. So I'm going to do the same thing I did before. I'm going to say x minus 4 needs to equal ax plus b at x equals -2. But then I also need ax plus b to equal x plus 2 at the point where x equals 1. Okay. So I'm going to plug in x equals -2, and I'll get -6 equals -2a plus b. And then I'll plug in x equals 1 over here, and I'll get a times 1 plus b equals 1 plus 2. And this is going to be my 2 linear equations that I'm going to solve using substitution or elimination. So I've got -2a plus b equals -6, and a plus b equals 3. I'm thinking I'm going to double the second equation so I can have -2a and positive 2a. Positive 2a, positive 2b equals 6. Okay, because I had to double everything. I'm going to add these together. I'm going to get no a's, 3 b's equaling 0. Okay, that's telling me b needs to equal 0. But then I go back to the easier looking at my 2 original equations. I see a plus b equals 3. That means a needs to equal 3. And there I found the values of a and b that make the function continuous for all x. I think that's all I got for you for this lesson. I really just need to show you how we graph a piecewise function, what it means when you see that curly brace. And now at this point, you just need to practice this on your own. Sketch some graphs, look at some graphs, and write some definitions. That's it. So that's all for this video. Thanks for watching.